video lab. So to start off, in our first lab, we previously calculated the electric force and charge coming from a charged tape. We then coded a simulation of this scenario and represented each charged tape as a pair of point charges. Now we want to redo this simulation, but with the charge of the tape being represented by a line of charges as opposed to a single point charge. So we're going to distribute the total charge over the length of that line. And hopefully this will help us gain a more accurate result for the charge of the tape because we use the simulation to help calculate the charge of the tape. So there is a lot of prerequisite information that you need to know in order to understand this lab. So the first being the structure of the lab, especially the original experiment, was to get a piece of tape to float. And then once we get the pieces of tape to float using another piece of similarly charged tape, we then calculate the charge from that. And what allows us to do this is Newton's second law, which is like the net force equals mass times acceleration, but more specifically, the net force, the summation of all the forces on that point. So if the tape is floating, then that means the net force must be zero because the acceleration is zero, which means all of the cumulative forces on that charged piece of tape should add up to zero. So in other words, the electric force, or the magnitude of the electric force and the magnitude of the gravitational force should be equal but in opposite directions. And to help us calculate the electric force, we use Coulomb's law, K/Q over R squared times R hat. We'll also need superposition, which effectively means that electric field at a point is the electric field at a point is a summation of all the individual electric fields at that point. And we also need the Coulomb's constant, which is 1 over 4 pi epsilon naught. The central idea of this lab is that we're comparing gravity to the electric force that the charged tape is experiencing. And we know the net force should be zero because the charged tape isn't moving, it's floating in stasis above another piece of charged tape. So the force of gravity on that tape should be equal to the electric force that the tape is receiving from the equally charged tape beneath it. And to calculate that electric force, we're setting it equal to the force of gravity, and the electric force should be a summation of every other electric force, at that similar area. Before I explain my code in further detail, I want to clearly state what assumptions I'm making and possible sources of error. So we assumed no air resistance would play a factor in this experiment. We assumed each tape had the exact same charge because in our first experiment, we created the tape the exact same way. And we also assumed that the charge of the tape is equally distributed along the line or length of the tape. And that in this experiment, we're representing the tape as a one-dimensional line. So in our code, I know the code's a bit hard to read, so I'm going to explain it in words. We're distributing a charge evenly along the entire length of the tape. And in this experiment, we're splitting the length of each tape into n amount of point charges, n being like a number we can change later. And we're iteratively adding up all the forces from each point charge on the bottom tape to the top tape. And then we created a simulation to simulate this process. So we're pretty much iteratively finding the net charge or the net force exerted on the top tape. And we know for a fact that this should be equal to the bottom tape. So using some algebra, we're able to find what charge it need to have for this to work. Help us find the electric force exerted on each bottom charge to the top charge, we use the electric field function or an electric field function that we first made in our first lab. And then we called it for every charge in the line and iteratively summed up all those small forces into the total force over the entire line. And then we compared that force to the force of gravity. And if our calculation for the charge is correct, then the net force should be zero. So the force of gravity, or the magnitude of the force of gravity, should equal the magnitude of the electric force. So here's an example of my code running. I can't really provide a video because the code, the net force is zero, so nothing's moving in the video. But we can see how the magnitude of the electric force and the magnitude of the gravitational force are about even, and we have a number displayed for the total charge resulting from this simulation. Each of the tiny green lines that you see represent the net electric field at that point, and you can see how it's sort of evenly distributed amongst the top. And all of those little green lines add up to the magnitude of the electric force, which happens to equal the magnitude of the gravitational force at the charge you see below. To get the charge from this lab, I actually have to do some extra calculations that I don't have time, but in the abstract for this video lab, I have a detailed explanation of how I got the charge. To answer some additional questions, what if we had modeled this lab with a point charge like the previous simulation? Well, luckily we've done this before. The necessary charge to make the tape levitate would increase from 1.528 times 10 to the negative 8 to 1.476 times 10 to the negative 5. And why? This is because we have to, when accounting for the length of the tape, this changes the total charge that we'd need. So in conclusion, our current simulation where we're calculating this tape as a line as opposed to a point charge should be more accurate and thus yield a more accurate representation of the net charge of the tape. That concludes my physics lab. Thanks for watching.